Okay, maybe we can get started. We are very happy to have Sheikh-Jabbari with us today. He's going to tell us about charges in general relativity and black hole thermodynamics. Yeah, please.
Okay. Thank you for having me here, and it's great pleasure to be talking to you about my two recent papers in collaboration with my students and postdocs. So it's about a very long-standing problem in general relativity, and I think we have a new sort of viewpoint on this, which allows to understand some of these long-standing issues there better. And then we apply this, what we have learned about the charges through the formalism that I'm going to present to you. We'll apply it to black hole thermodynamics and see what new we can learn on that. So let me start with reminding you of two very basic features and important features of general relativity, namely equivalence principle, which is manifested through general covariance in the space-time, and background independence, which means that all geometries where all the other fields and the physics are formulated upon are solutions of the same theory. And we usually focus on the general covariance, but discuss less on the background independence. And I'm going to tell you more about the background independence. And basically, the statement is that it could be also viewed on the same footing as general covariance, but on the field space, on the space of solutions of the same theory. So as we'll see, this standard equivalence principle and background independence are general covariances on space-time and solution spaces. And in the viewpoint that I'm going to discuss here today, the reason why we have not been able to define covariant charges in GR, or the main issue there, is because we have sort of gave less importance to the background independent issue.
Sorry, can I ask a question here? Actually,
Please,
Shaheen, already.
please.
General, what you're calling diffeomorphism invariance is really diffeomorphism redundancy. It's the fact that there are multiple coordinate systems you can use to describe the same physics. But
Yes,
solutions are different states, right? They're physically different. Like we don't say one
yes,
solution is the same as another solution.
yes, yes, that's
So
right.
I'm a little confused. If you could go back to the previous slide, please. Isn't it somehow different from general covariance? Yeah, that's right. Isn't it somehow different from general covariance? Because
No,
if I
no, it is, but there are important details that I'll discuss in detail. Okay, so that's a very good question, but uh, I'll discuss this. Okay.
Okay.
So, and of course, just maybe there's no need to remind you of black holes that are consisting a large class of solutions to GR, or any generally covariant theory of gravity, in fact. And black holes are usually characterized by a null surface separating space-time into inside and outside the horizon. And black holes are localized objects. One can hence try to specify them through the charges like mass, electric charge, and angular momentum. And it's very well known that black holes obey laws of thermodynamics, and in particular, they have entropy. And again, like in usual thermodynamic systems, black holes are expected to obey something which parallels Gibbs to Hem relation. That's a small relation. So Ayer and Wald in 1994 provided the first principal derivation of the first law of thermodynamics for stationary black holes with a Killing horizon. It's very elegant. It basically relates first law of thermodynamics to diffeomorphism invariance of the theory. And it builds upon the walled entropy, which is now treated as a Noether charge. And there, as I'll discuss, there are some shortcomings of Ayerwald derivation, and basically I'll discuss how our viewpoint and our new formulation generalizes or addresses those shortcomings. And I'll also give you a first principle derivation of small relation for a generic black hole. Okay. So the setup that I'll be discussing, my formulation is covariant phase space. And basically, it manifests diffeomorphism invariance on the space-time. And also, it allows me to manifest the same, please.
On the previous slide,
Uh-huh.
it's kind of like what Suvrat was asking, but in this context, the first law refers to, if you change the mass of the black hole, that means you're actually changing the geometry, and it relates it to the change in the area. But this diffeomorphism invariance is a redundancy in one given geometry. So how can these two be related? Could you say a bit more?
No. It's basically the first question to ask is whether the notion of the mass that you're talking about is rigorously diffeomorphism invariant.
But that the ADM mass is, right? If we look at infinity, then
so there are important details. As you mentioned, for example, you have ADM mass. It only applies to carefully defined asymptotic flat space-time, whether it applies to other asymptotic behavior of the space-time, whether you can define it without going to the infinity. And there are lots of important details. And the question is whether those details actually respect general covariance or are diffeomorphism invariant.
But I mean, here the setting is just stationary black holes, right? With a killing horizon. So for them, all these notions of mass should probably agree. You cannot.
Not really. Not really. Let me give you one simple example. So, for example, not for the mass, for the mass, maybe there are less issues, but there are still. But for angular momentum, even for usual classical mechanical systems, you need to, for angular momentum to be in a specific frame, and it is frame dependent, right? Different rotating frames would measure different angular momenta or the usual momenta. So it's not clear that the notions like mass angular momentum and other things are really generally covariant.
Okay, I was just asking this bullet point that you have under Ayerwald, that it's connected to the first law of diffeomorphism invariance. The first law is connected to this. So could you say just a bit more what the connection is?
Sure. This will be the main topic, but of the talk, okay? But as I was trying to emphasize, these are neither of them are trivial. Just bear in mind that the notion of conserved charges or charges, mass, angular momentum, and any other charge in general relativity is in principle not well defined, even for stationary black holes. They are frame dependent.
Okay.
And this is, and also in general relativity, the notion of energy or energy momentum tensor is also ill-defined. Exactly because of diffeomorphism invariance of the theory or general covariance. Okay, so these are very long-standing problems that have been discussed in the last century. But the claim that we have is that through this variation or a generalization extension of this covariant phase space method, we are able to address these long-standing questions. So bear with me for a second. I'll discuss all. These are all very relevant and good questions, but I'll try to formulate them through this covariant phase space method. So may I move on?
Okay.
Okay. But I'll discuss the questions you asked. So in the covariant phase space formalism, as the name suggests, is a covariant formulation, meaning that it does not depend on the specific choice of time or other coordinates for defining the charges. You may view it, as far as the charge is concerned, you may view it as an extension of Noether's theorem. And it basically provides a setup to define surface charges associated with local and global exact symmetries. And I'll say more about this. This formulation has been in development in the last 30, 40 years. So these are some milestone papers. And of course, you can see my book with Daniel Grumiller on black hole physics for a summary. So this is the outline of the talk. I'll review basics of covariant phase setting. I'll extend the covariant phase space to the cases where the boundaries of the space-time can also fluctuate or allowed to fluctuate. And so this is the covariant phase space with fluctuating boundary. And basically, I tell you how this extended formalism sheds light on the problem of charges in GR in general. Then I'll try to apply the lessons that we have learned through this to the questions regarding black hole thermodynamics. I propose 4 theorems, propositions, and then provide a rigorous derivation for generalized Fresh law and generalized small relation. And I'll end with some concluding remarks. Okay, so this is a quick review of covariant phase space formalism, and hopefully this will address some of the questions you asked and sort of frame the setup that I'm going to discuss. So in physics, we typically deal with a Cauchy problem, which means that the dynamics of the system is uniquely determined by initial data on a partial Cauchy surface C. So you may view this as a constant time slice. Then basically you have a set of solutions. You may show that there's this set of solutions form a phase space, and there's a well-defined symplectic form over this solution space. And basically, usually the symplectic form is defined by an integral over the Cauchy surface, constant time slice. And but the point is, generically, when we have a generic problem in physics, besides the boundary, besides the Cauchy surface, the initial data surface, we have a boundary, which is a null or time-like surface, like, for example, the boundary of the ADS space. So this is a codimension 1 surface. And in general, hence, we deal with the boundary plus initial value problem instead of just initial value problem. And the question is, how do we deal with this more general setup? Okay. Going back to the questions you are asking, probably when you asked the questions, you had in mind the initial value problem, but the boundary data is also essential to specify the solution space. Okay. And I want now to present to you a formulation which sort of covariantly and rigorously deals with this general setup. initial and boundary data may be rearranged through symmetries, and these symmetries are basically, for the case of GR that we are interested in, is a measure zero subset of diffeomorphisms. So just going back to the first question Subrat asked, not all diffeomorphisms or all coordinate transformations are non-physical redundancies. There's a measure zero subset of them, which are physical. They basically they could be used to find some representations for the initial data or the boundary data. And Noether's, the standard Noether's theorem relates symmetries to conserve charges, and this measure zero subset of diffeomorphisms could be also used as symmetries, as I'll discuss, on the solution space, which means that they take one solution to another solution. And you can apply Noether's theorem to this more general notion of symmetries. But the point of the usual Noether's theorem is that it's not covariant over the space-time or on the field space. As you know, Noether's theorem relies on a very particular notion of time, which basically breaks covariance of the charge, and it's defined for specific set of solutions with a given background, so it's not covariant over the field space either. So
Sorry, can I ask a question here?
Yes,
Shine, usually if you want to do gravity, even then, we want to be in a situation where we fixed at least the asymptotic boundary conditions. And then, we do have a notion of time, and there's some asymptotic symmetries, and the Noether charge is covariant with respect to those. So here you have some more general setup in mind where you have not fixed the asymptotic boundary conditions.
Yes, I have a more and that's exactly the point. Exactly.
Okay.
And I'll discuss implications for the cases that you also asked, but that's exactly where I'm going. So, and usually Noether charges are integrals over codimension 1 surfaces, constant time slices. However, when we have local symmetries and the symmetry generators, which are subject to the Noether's theorem, are a part of this, the physical part of, I'll define this more carefully later, the physical part of the local symmetries, then the Noether charges, the integral, which defines the charges, becomes a codimension 2 integral. A prime example of this is the usual Gauss law in Maxwell's theory. So when you have a J mu, a conserved current, electric current, you can define, you can integrate the zero component of the time component of J mu over a constant time slice, and it defines the charge. But you can use Maxwell's equation and rewrite this as an integral over the electric field over a sphere, a codimension 2 integral. And this is a very general feature which appears for any theory where the charge is associated with the global part of some local symmetry, as in the Maxwell's theory. Okay, so basically this covariant phase space method is applied to these cases where we are dealing with the genuine symmetries are a part of the local symmetries that we have. So the charges are given by surface integrals. So in my seminar, codimension 2 surface is denoted by S, which is the intersection of a boundary and a partial Cauchy surface C. So boundary and B and C are codimension 1 time-like or space-like, respectively, surfaces, and S is the intersection of them. So just to have this picture in mind, the general setup is that The question I'm asking is, I want to formulate a theory like gravity, general relativity, in a box. So this box could be an arbitrary section of the space-time, as you can see in this pinkish region, the cylinder type region. And the boundary could be an arbitrary section of the space-time. So I assume that there is a bigger space called M, and that M does not have any boundary. This is just some hypothetical space. Then this box that I want to formulate my theory on is embedded into this boundaryless space. This C, the green surface, is the partial Cauchy surface. You may view it as a constant time slice. The vector C is normal to this surface. Then we have the boundary, basically on the cylinder, the B is the boundary, which is a time-like surface, and this vector little b is the normal to this surface. B and C vectors are not in general orthogonal. It depends on the choice of the time coordinate or space coordinate. But this n, I choose it to be a vector which is orthogonal to B. Okay, so B and C are forming a two-dimensional subspace of this space, and this which is transverse to this codimension 2 surface S. Okay, so that's the picture to keep in mind. And you can basically let this be the boundary of this cylinder to go to infinity, for example. So, but I'll keep the setup very general. Okay, so this is the kind of setup that I'm interested in. So covariant phase space.
So I can ask a question here,
Please,
Shine.
please,
I
please.
got disconnected at the beginning of this slide, but is this picture? What is the gauge invariant specification of this manifold, of this boundary of this manifold? You know, if you're trying to compare different backgrounds or different solutions, then how do I say, you know, in one geometry this boundary is the same as what it is in the other geometry?
Okay, so this is the kind of question that I'm going to ask, and this is how we are extending the usual covariant phase of space, where we allow for generic fluctuations of the boundary.
Okay, but could you give a quick preview of how you would define this boundary? Like, what is the, I mean, I thought this is always, yeah.
Okay, so basically, well, we usually define the initial data on C.
Yeah.
Okay, and so this is a part of the definition of the problem, right?
On C, this is part of the definition of the problem, but the boundary extends in time, right?
Boundary extends in time.
And so how do I specify what the boundary, like what is the gauge invariant way I specify the boundary?
Well, the same way that you choose your C. So, for example, you can take your time coordinate to be exactly the one which is in usual, for example, 3+1 decomposition of in ADM decomposition. You do it through shift and lapse functions or vectors. Okay.
Okay.
The same you can do, or you should do with B.
Okay, I mean, maybe I can ask again when you, yeah.
But the same way that you define your C, you can define your B. Maybe since you're used to this ADS case, you can view this problem in the ADS.
In ADS, actually, usually you define the boundary only asymptotically. You say, look, you look at the metric and there is a regime which is, you know, and you kind of demand that on the metric where you go very far away, and in that regime from, you know, you find that there's some asymptotic geometry. But the problem in defining it for a general case is that it's much more confusing, right? We could say,
Well, you can just to avoid these questions from the start, you can say, I want to formulate my theory, for example, general relativity in a box. And then in the room that you are sitting, and you can then ask. So you can take the definition of the room to be a part of the definition of your problem, right? That's always what we do, for example, in undergrad Maxwell's theory, electrodynamics, right?
Yeah, I mean, usually the physical argument that's given against that is that gravity can cause the walls of the box to fluctuate. That's
Yes.
why we work in ADS, right? Because ADS is a good way of doing gravity in a box, but doing gravity in a finite box is generally not such a good thing to do.
Yes, unless you allow the boundaries to also arbitrarily fluctuate.
Okay. Okay, yeah, please go on. Yeah, I can ask again.
Yeah. No, so the question you were asking is, how do you specify your box, the initial or boundary data? But that's a part of the definition of any problem that you give me. Besides the action of the bulk theory, like general relativity, you need to tell me what are the initial and boundary data that we have. Exactly. And okay, so that's basically, let me go back to this covariant phase formalism. Uh, uh, it has some caveats. Covariant phase space formalism yields charge variations over the solution space and not the charges compared to the Noether theorem. Noether's theorem basically gives the charge itself. And then one should ask whether these charge variations are integrable over the solution space. The second thing is that Noether theorem it has some ambiguities in definition of the charges. For example, if you shift the theory with a boundary term, a total derivative term, the Noether charge would change. So the question is basically how these ambiguities or freedoms in defining the charges enter into this covariant phase space formalism, or how they are dealt with here in this. So the objective, the first objective of this seminar is to extend and generalize the covariant phase space formalism to the cases where the boundaries are allowed to arbitrarily fluctuate. And what I'll show is that this is the main statement of the first part, that if once you did so, the charges become integrable. Okay. Before going on, let me emphasize the fact that the boundary versus corner. So basically, just going back to this figure, basically, boundary is a time-like surface, like this P. When, for example, these are the walls of the room that you're sitting in. And this S is a constant time slice over these walls. Okay, so this is a codimension 2 surface. And here, hence, we have a corner. So this S, you may view it as, since it's codimension 2, you can view it as a corner in the space-time. Okay, so in general relativity, because of the diffeomorphism invariance, as you know, there are some issues with defining conserved charges covariantly, and locally. And people have tried to address these questions through, for example, Brown-York formalism, the quasi-local, and they have defined quasi-local charges. These are basically charges defined over this codimension 2 surfaces over the corners. So that's basically what I'll also be focusing on. Some extension of Brown-York, if you wish. And the same ideas have been tried to explore, in particular by Jacobson and collaborators, and trying to show that if you have all this the needed data on codimension 2 surfaces, it's enough to basically specify the dynamics of the whole theory It's some sort of version of the standard ADS-C CFD, if you wish. But it's more general setup, and it need not be done on ADS or in the some space-time with some given asymptotics. So that's the general idea. So that I just wanted to basically mention some of the ideas that has been floating around. So let me just, after this long discussion, let me just start with some equations. Consider a d-dimensional spacetime spanned by coordinates x mu with metric g mu nu. Let these two surfaces, the boundary and the Cauchy slice, or partial Cauchy slice to be more precise, be denoted by b equal to 0 and c equal to 0. These are two scalars, if you wish, two scalar functions, b and c. And MB is the part of spacetime, as I just showed, which is limited to b bigger than 0 and c bigger than 0. So that's in this figure. This is this part of spacetime. Take this S and above that. So that's basically because here where this M, B, and C intersect is the initial time, if you wish. And I want to study the evolution of this. Okay. Okay. So, and I take this S, which is the intersection, to be a compact, topologically compact codimension 2 surface. By which I mean I'm going to drop the integrals over that, over total divergences, okay? And moreover, I'm going to assume that all the functions are smooth over S. So as I just mentioned also on the figure, the normal vectors to this surfaces B and C are simply given by gradients of functions B and C. And these vectors are not necessarily orthogonal, and the angle between them is parameterized, could be parameterized by A. So in principle, the metric on basically two-dimensional part of the spacetime spanned by this B and C vectors has three entries. One of them is B, the other is C, and the third one is A, the basically angle between these two axes that I have chosen. The metric on the boundary will be denoted by gamma mu nu. So that's basically the metric on the S, on the codimension 2 surface, will be denoted by Q. Okay. Okay. So there are some standard conventions. The square root of determinant of metric over d dimensions is related to two-dimensional codimension 2 square root of determinant of metric and the determinant of metric over the boundary in this way. These are just standard. And the binormal to this codimension 2 surface is given by this epsilon mu nu. And just for the conventions.
Sorry, Shaheen, I missed something. I must
Please.
have lost track. B was the boundary and C was a corner which you defined as the intersection of the Cauchy boundary.
S is the corner. C
S is the corner. Yeah, S is the intersection of C and B.
Yes, exactly.
Now, where did the degenerate metric come in?
There is no degenerate metric.
You said degenerate metric, or this Q is yeah.
This is codimension 2. So this is the metric on the S, if you wish.
Okay, that's just the metric on S. Okay.
Yes.
Okay.
Well, it is degenerate over the d-dimensional spacetime, but it's a good metric on over d minus 2 dimensions.
Okay.
Yeah.
Okay, thank you.
Yeah. Okay. So I have codimension 1 and codimension 2 integrals over and this is just a shorthand notation for this two integrals. Okay. Okay, so still going with the mathematical setup. Besides the geometric quantities that I just mentioned, I deal with the generic fields over the spacetime denoted by capital phi. Then by delta phi, I denote generic variations of phi. These are one form over the field space, okay? Then I'll be using the notion of PQ forms, where I have a P form over spacetime and a Q form over the field space. For example, epsilon mu nu that I just showed is a 2-0 form. It's a 2 form over the spacetime. It's a 0 form over the solution space. And delta A, B, or C are 0-1 forms. A key quantity, a key object in my analysis will be this chi, which is a 1-1 form. It's defined in this way. It's a 1 form over the space-time and 1 form over the solution space.
Are you using solution space and field space interchangeably?
No, but field space is more general and solution space is a part of that which solves equations of motion.
Okay.
Okay. So far, since I have not talked about the equations of motion, I'm calling them field space, but later on in a couple of slides, I'll be focusing on the solution space. Okay. Yet I've not imposed on shell, but I'll do so. Okay. Now it comes. So this starting action is an integral over this MB, just a part of space-time, if you wish, a box. And the trick that I'm going to use in the analysis is that I replace this box with a boundaryless M with a delta function. So this H is the Heaviside delta function. For example, H of B is basically Heaviside over B. So it basically captures whatever inside B.
Sorry, Shane, this I didn't understand at all. I thought the starting action should be that of general relativity on the full manifold.
Yeah, what's full manifold?
I mean the manifold in which this the whole C and thing was embedded, right? In which C and B were embedded.
No. Basically, my problem is defining the theory or studying the theory over MB.
I see.
I want to study gravity or general relativity in a box, in a very arbitrary box.
I see, but we can't even define MB till you give me the full manifold, right? Is there a good definition of this?
No.
I thought this is defined by saying that I give you the full manifold, and within that there is some boundary which has some form.
You can do this, but I actually avoided that because then you would be worried about the asymptotics of that M.
I see. And the other thing I got confused was I thought above you were using this covariant phase space formalism. But when you use the covariant phase space formalism, I thought you say that the phase space is the set of solutions to the equations of motion.
Yes.
But shouldn't all this while I was assuming that the equations of motion were those of general relativity. But now you're saying that you want a different action. So how did you define the phase?
No. This L is just a general action. You can take it to be Einstein-Hilbert.
But the solutions that you had earlier were solutions to the action on the full manifold, right? Not the solutions to action on a submanifold.
Well, the problem that I'm interested in is solving equations of motion in a box. And if you want to, and I don't want to know actually what is outside the box.
But I mean,
this box could be extended to the, well, if we have a local theory, this must be possible.
Because the information could come from outside the box and hit the box.
Right? No, that's the whole point. That kind of information, it should be possible to put all those kind of information that you're talking about on the walls of the box. Otherwise, the problem is not well defined. I mean, this is a very basic question, right? I don't want to know what is outside the box, and all the needed information should be, I should be able to provide it as the information on the wall.
Okay, maybe that's where we would like to end up, but it's not clear to me that such a description always exists in gravity. So can we show starting from, yeah.
Why not? If it is a Cauchy problem, it must be.
If it's a Cauchy problem, it just says that we specify the full Cauchy slice and I can evolve upwards. It doesn't say that I can cut out part of the space-time and put some effective boundary conditions, and that will somehow, also.
Not if so. This is a question about existence of solutions to some partial differential equation. And as far as the formal setup of the problem is concerned, I don't see if the Cauchy surface is not a constant time slice, but something like a time-like boundary, there shouldn't make any difference as far as differential equations are concerned.
Okay, what I'm worried about is just physically something that's happening outside this box could affect the boundaries. Maybe it makes the boundary collapse into a singularity or something. So how do we
okay, so well, as I said, there are some different versions of the you can define different versions of the problem. For me, just the simplest setup is that I want to formulate, for example, Maxwell's theory in a given box, and I don't want to know what is outside the box.
So for Maxwell theory, clearly this can be done. But here, the kind of concern I'm worried about here is you're trying to do this effective theory. Someone sends a huge shell of dust from outside, which collapses into a singularity inside this box. Therefore, this whole boundary and so on stops existing, right? And that's because of some action of somebody who did something from outside.
Well, all the information about that action should be able to, I should be able to put it as something on the walls.
Okay.
Right?
Okay. This I'm not asymptotically we say this, right? We don't allow for things that destroy the asymptotic boundary, but for finite boundaries, it's not clear why. Yeah. Okay.
But just as far as mathematically, the problem, if you're not worried about the singularity, let's put that aside for a second, then I don't see any difference between Maxwell's theory and general relativity. The equations are much more involved, that's fine, but the basics are just the same. This is a local partial differential equation, and it must have solutions, provided that I give you the appropriate boundary data.
Okay. Please go ahead.
So if I now let's just move on. So the trick is basically I remove this boundary by putting this heavy side, and this M is very arbitrary, and nothing in my description actually really relies on the details of what this M is, apart from the fact that this MB is just embedded into that. And so as usual, once you have the action, you basically find the variation of this to define the equations of motion. And but now I need to also consider this heaviside delta inside the action and do the variation over this h of b. And this basically gives me the usual equations of motion, E of phi times delta phi, plus a boundary term. And this boundary term has now two parts. One is the usual part, which is called Lie-Wald in this context. And then there's a part which is coming from the variation of this h of b, the fact that I'm allowing for the boundaries to also fluctuate. And the same vector chi appears here. Remember that this vector chi was associated with the fluctuations of this B and C, which define the boundary of the spacetime. Okay. Then
what is this LW, theta, mu, LW?
I'll show it in detail, but this is called the Leewald theta. Theta is basically when you have any Lagrangian and you vary it, the bulk part, which is this one, it gives you the equations of motion, and then there is a total derivative part, which is defined at the boundary. Okay, so this is basically take for example a free scalar theory, d mu phi squared. When you find the variation, it gives you the equation of motion plus a part which is d mu phi delta phi. That's the
Like
this
E
theta.
delta Q for a particle.
Yeah.
Okay.
Yeah. Exactly. So, but now the reason I have this extra part is that I'm allowing for the boundaries to fluctuate. Normally we don't do this, and this appears through the variation of this h of b that I've put here. Okay.
Is this for a particle that's moving on a line, like just a, and so does this mean that you're allowing the endpoint of the particle to fluctuate?
Yes.
Some trajectory from T initial to T final, and
exactly, and you allow for the T initial and T final to also vary. Exactly. Okay, so then delta S equal to 0 yields equations of motion. Please.
Yeah. If you're allowing for the boundaries to fluctuate, how will you state your action principle really when you set delta S equals 0? I mean, what we usually do is we set the variation at the boundary to be 0 and then get the bulk equations of motion. But what do you mean by an action principle now?
Okay.
You're not fixing the phi as 0 at some boundary point?
Yes. So actually, I was careful not to use action principle. So I found the variation. And delta S equal to 0 yields equation of motion, but I'm not going to impose this extra piece also to be equal to 0. So in the usual field theory, as you correctly mentioned, this yields boundary conditions. I'm not going to impose the full action principle if you want.
So you'll not also impose any boundary condition on delta phi?
No, I'll try to keep it free, and maybe later we need to deal with that. But as far so far, it's free. Okay, and this part actually it will be very useful in what I'm going to tell you. So I'm just requiring field equations, but not delta S to be exactly 0. Okay. Then if you start with this theta mu, you can find its variation over the field space. That's basically delta theta mu and denoted by little omega mu. So it's this theta by definition was a one form over the solution space because it appears through delta S. And this omega is a two form over the solution space. If I use the form notation over the space-time, it would be dual to d-1 form, okay? But let's keep it as a vector, okay? By definition, delta omega mu is 0 because it's delta of something. And the important part is that this divergence of this omega mu on shell is 0 if I also assume delta phi satisfies linearized equations of motion. Okay. So afterward, what I'll mean by on shell means imposing equations of motion in the bulk, plus basically assuming that delta phi variations also satisfy linearized equations of motion. Okay. One can show that this is
explain the notation of omega mu, and then in the bracket there is delta phi, semicolon phi.
This means that it's a two form over the solution space.
And what does the semicolon phi mean?
Oh, besides this two form, I mean, this also depends on the configuration on the phi itself, right?
But if it's a two form and you're giving it equal argument, shouldn't it be zero?
No. It's so this phi is a generic field. It's not a single field, right? For example, delta of metric G mu nu. So it has different components. Okay. So it's a formal notation. This means that it's a two form over the space solution space, and the components of this two form depends on the phi, on the field configuration.
Is a two form on the solution space and a one form in space time?
It's a vector on the space time, but instead of the vector, you can say it's a d-1 form over the solution space, over the space time. Okay. So formally, if you wish, this omega is a d-1, 2 form. Okay. But the important part about this omega is that it satisfies, its divergence is zero on shell because of what I've written here. And so this omega is divergence free and is also closed over the solution space. And now I'm using the word solution space because I'm I'm restricting myself to solutions of equations of motion plus allowing for only variations which satisfy linearized equations of motion. So basically on the solution space, you have this surface in the field space, which is called solution space. And I'm going to also impose this condition that the tangent to this solution space, namely delta, is also satisfying this linearized equations of motion. So this is a condition on the tangent part of the solution space, tangent vector to that, or cotangent if you want to be more precise. Okay, now since based on this omega, I can define the symplectic form by integrating this omega, which is a vector, over an arbitrary Cauchy surface. Okay, one can immediately show that omega does not depend on the choice of the C, and that its delta is zero. This means that omega, which is 0, 2 form, is exact over the solution space, and it is invertible. So actually, this means that omega provides me with a well-defined symplectic form over the solution space that I just defined. If I just plug what I had for the action that I started with, one can see that it's just a straightforward computation, that this omega has a part which is given by a codimension 1 integral over b, the Leavold part, and a corner part, omega c, which is given by an integral over s. And it depends on this chi. So had I just fixed the boundary and did not allow for B and C to fluctuate, I didn't have this corner. When you go through the standard covariant phase space papers in the literature, they only have this part. They don't have this corner. So this is, I'm allowing for my boundaries, B and C both, to arbitrarily fluctuate. Okay, so let me discuss also the freedoms. This is, by the way, as there was a question, could be applied to particle dynamics as well as field theory. And this gives me a way to formally define symplectic forms based on Lagrangians without going to the Hamiltonian or the phase space directly. Okay. And this is why, and the covariance of the formulation is relying on this fact that it did not depend on which C you choose. So any time coordinate that you could choose leads the same symplectic form. This is where the name covariant phase space comes from. But this is a very formal way to define symplectic forms over solution spaces covariantly. The freedoms that I just mentioned, one of them is the W freedom or ambiguity, if you want. One of them is basically you could have shifted your Lagrangian with a total derivative. It would not have changed the equations of motion, but apparently it changes this theta that I mentioned. And the other one is the Y freedom, which is basically shifting this theta mu, also usually called symplectic potential, with a total divergence there. So, but the point is that neither of this first one does not appear in the omega that I just defined, because you're taking another variation over this and it just drops out. Okay, so a symplectic form is independent of the W freedom. It's free of this ambiguity, but it depends on the choice of Y. To put these ambiguities together on the symplectic potential theta, it means that I need to shift theta in this way because of these ambiguities or freedoms. This part is, which is again proportional to the chi, is something that you don't find in the standard covariant phase space formalism in the literature. Okay, but the point is, if you go through the computations, symplectic form only depends on a certain combination of this Y and W, which is this Y bar. So in the absence of chi, standard covariant phase space literature, the statement is that omega is independent of W, but Y actually appears, the choice of Y appears in the symplectic form. Okay, so this is the general setup so far. But let's see how can I use this to define charges. When you hand me the symplectic form of any theory, let it be, for example, a particle theory, and you give me some specific variations associated with some symmetry, like let's call it delta xi of phi, then I can basically compute omega over this delta xi of phi, and this is basically what we usually call charge variation, to be more precise. I have used this notation delta slash to emphasize the fact that what you get from here is not necessarily an exact one form over the solution space, meaning that this need not be integrable. There is no Q that delta over that is given could be equal to omega. So this is the most general case. So this formulation actually gives me the for any symmetry generator Xi, which generates these transformations over the fields, gives me the charge variation in this way. I can rewrite this in terms of this omega that I introduced earlier. Recalling that omega had zero divergence, this means that locally on shell, there exists a d minus 2 form or k mu nu with upper indices, antisymmetric bivector, where its divergence is giving me omega, just Poincare lemma. Then you can plug this into the definitions that I gave above, and this gives me the charge variation as a surface integral. Okay. This is basically how I get surface integrals for the charges rather than the standard Noether theorem because of this. Okay. Let me remind you of, for example, the example of Maxwell's theory. This omega mu could be current, and this k mu nu is just the F mu nu, the field strength in that case. And this is the equation of motion itself. please. Was there a question?
Delta phi, yeah, this delta phi, phi includes only the coordinates or also the momentum?
This is okay. I had a solution, a generic solution. So this phi now, since everything is on shell, is denoting all possible solutions with a given set of boundary and initial data. And this symmetry generator psi moves me in this solution space. So it takes symmetry by definition, as is defined in the Noether theorem, takes one solution to another solution.
I'm asking, like, in a particle example, would phi just be Q, or phi would be Q and P together?
Okay. In that case, actually, it would be both. But if you if you want to think about this more covariantly, take Q, not P, and take all the set of all solutions with all possible initial values. Okay. Then this is enough to specify the full X and P, Q and P. Because one of those initial values is the initial momenta, or the time derivative of your Q over a constant time slice. Okay. Is it clear, or?
Reason I'm asking is, you mentioned this covariant phase space is the space of solutions, right? So it's already the space of solutions.
Yes.
Then what does it mean to have a phi which does not satisfy the... Is phi a point in the covariant phase space or not?
Well, phi is a specific point, yes.
In the covariant phase space?
Yes, yes.
So doesn't it always represent a solution to the equations of motion?
Yes. So it also depends on initial data in your example of particles. And that initial data, besides Q at Q0 at some time, it also depends on the momentum, or Q dot at 0, right? So delta phi in this sense means moving in the space of initial data.
But I mean, what does it mean? Because you had some things, then delta phis that are not satisfying solutions, that are not satisfying the equations of motion, right? Like earlier.
No. So that was a couple of slides before, and after this slide, actually, I always impose equations of motion.
Okay.
Sorry, I didn't emphasize that. As well as assuming that delta phi satisfies linearized equation of motion. So that's what I call on-shell.
Okay. So basically, this delta operator, I should think of it as the exterior derivative on covariant phase space.
Yes.
Okay.
Yes. So but just to sort of simplify things, this for me, this delta is acting on the set of all possible initial data that I need to tell you. And for the case of particles, for the case of fields, besides the initial data, I need to also tell you what happens at the corners, at the endpoints of your Cauchy slice.
Yeah, but that full specification of the initial data is in a one-to-one correspondence with the solutions, right? Like,
exactly. But initial plus boundary data. Yeah. Okay. Yeah, exactly. So, and this variation is basically moving me in this set of all possible initial plus boundary data, if you wish. Okay. So then...
Shaheen, a brief note about maybe it's been roughly an hour. Maybe you can take 25 minutes more.
Okay. Yes. Sorry for going over time. So I thought it's okay.
You're not over time. Yeah.
Okay, good. I'll be done by that. Thanks. So this here I have this 0, 1 form, And if it is integrable, then this means that there exists a Q where I can write this delta slash as delta. But it's non-trivial to show that the charges are integrable. And since this definition of the charges is built upon omega, it's invariant under the W, shifting the Lagrangian with the total derivative.
Sorry, Shaheen, can I ask just a remedial question here? In this context, what does integrable physically mean?
Okay. Integrable means exactly this one. So this is a 0-1 form. And the question is whether it's an exact 1 form.
I know, but physically, what is it? What would it mean for a charge to be integrable or not? What does that mean?
Well, if it is not integrable, there is no charge, right? Because I cannot define the charge. I can only define variations of the charge. I can give you one example. Let's suppose that, which is very relevant, and I'm sure you have thought about. Let's consider the example of general relativity on asymptotic flat space and take the boundaries to be scribe plus.
Yeah.
Then basically we have the boundary data, which are defined at I0 on the corner. And then besides that, you have the bulk modes, which can fly over and go through scribe plus, reach there.
Yes.
So the charges that you could define the surface charges, the BMS type symmetry charges, I mean,
yes,
are not integrable if you have these fluxes of the bulk gravitons passing through. This means that you cannot define the charges.
Non-integrability. Can't you define them by setting them to be 0 at scribe plus plus, and then just integrating them from there and just integrating the flux?
You can, in that way, you're giving me the variation of this. So it changes when, for example, you go from V1 to V2 over the scribe. But it doesn't give you the charge itself.
I see. What I understood right now is by integrable, you mean that in field space, if you go around a loop, then the value of the charge shouldn't change.
Yes.
I didn't, but what you said about the BMS charges, I didn't understand why that tells you in field space. The fact there's flux, so it's leaky boundary. But why is it obvious that in field space, if you go around a loop, you'll get a different value? It seems. I thought you could always define it nicely by setting boundary conditions at scribe plus plus, going back. That's not good, you're saying.
Well, it's not good enough. So basically what you get is variation of the BMS charges in that example is equal to the news, the Bondi news, which passes through the boundary.
This is a question of conserved. You're saying the charge is not conserved.
Oh, wait.
But being conserved, I thought is different.
This is a very good question. Please bear with me. This is actually one of the main parts of the talk. So, but I have some time limitation. But this is a very good question. And this is related to my comments about general covariance and background independence that I made in the start. Okay. So this is basically, if the charges are integrable, I can define the Poisson bracket of charges. Remember that I have symplectic form. I can define Poisson brackets, and these charges are some functions over the field space. So this is just standard Poisson bracket of two functions over the field space. Or the solution space, which gives me this is a theorem. It's just simple to prove this, that this is the charge of the bracket of the generators, plus potentially there could be some central terms. And by definition, central terms are things that have vanishing variation over the field solution space. Okay, so this is a theorem. It just follows from the basics. And then for my setup where I allow for the boundaries to fluctuate, besides the usual part, which is I've denoted by Leavold, I have this part which is coming from the corner fluctuations. And what I'll just show is that when I allow for the boundaries to fluctuate, the charges are always integrable. And the integrable charge is nothing but the Noether charge. Okay. So this basically ends up the question of integrability of the charge if you allow for the boundaries to arbitrarily fluctuate. So the way it works is that just one needs to look at the expressions. For a generic theory where this Leavold part could be written in this way. And here I'm assuming that my symmetry generators, like killing vectors, if you wish, for specific examples, to have zero variation, they're field independent. And this Q Noether is basically divergence of the that is giving me the Noether current, and the Noether current is defined in this way. Okay. So the point is actually, so this is just the expression for the Leavold part. I had this corner part that I need to add. If it were not for this part in the Noether's charge expression, and the Noether charges would have always been giving me the integrable charge, but because of this part, the Noether charge and the integrable part, I mean the charge that you compute through the standard covariant phase space do not match, and this is basically the main source of non-integrability. Sorry, this one, this. Okay. And then this is the expression for the corner part, which is proportional to this chi. So if I didn't allow for my boundaries to fluctuate, that's exactly what in the literature they do not allow. They don't have this corner part. One can just go through the standard algebra. I'll spare you with that. And just some straightforward algebra leads to this one, this expression for the corner part. And then I need to sum up these two to get this. Some parts actually cancel out, but what I get is this one, where J is the Noether current. And again, some massaging of this expression leads to what I'm going to tell you next. But just the main point is that the question is whether I can pull this delta out and put it just out of the integral. And since now I'm allowing for the fluctuations of the boundary where I'm integrating over, there is an extra part associated with fluctuations of this S that could be added to this or subtracted off when I push this out. And now, if I did this carefully, and that's what we did, what we'll get is that the effects of the fluctuations of the boundary is exactly going to be equal to this one up to some total derivatives that I drop. And hence, it will cancel out this. So that's basically the end result. So I have shown that when I consider fluctuations of the boundary, delta slash is always delta of something, and that something is nothing but the Noether charge. Okay, so so far so good. This expression is not only covariant over the space-time, because everything, all the indices are covariantly summed over, and the definition of S, it was covariant. This is also covariant over the solution space, because it's just involving some deltas. Some one form is equal to some delta of something. But so this expression is covariant both over the space-time and the field space. So this means that it's in my initial presentation. This means that it's generally covariant over the solution space, background independent, and also equivalent. It basically respects equivalence principle. But when you want to integrate this and write the expression for the charge, you need to basically introduce some integration of some integration constant that I've denoted by QR. And this is actually the source of the trouble with the definition of the charges in general relativity. Okay, because by definition, variation of this is zero, because I want this to be an integration constant over the solution space. But if I, to specify this, I need to give you a reference configuration, phi r, such that, for example, Q of phi r is equal to 0. Then when you plug this here and solve it, what you get is QR is basically Noether's charge for that specific configuration, so that the total charge is 0. And you can see that because of the appearance of specific background, the total charge expression is not background independent anymore. And it's not covariant either. So by covariance, I need to tell you what the general definition of covariance is. When variation of some generic field, which may depend on size, is equal to variation of that with respect to some diffeomorphism, for example, eta, is equal to the generic variation computed at eta. This is called covariant. This is just a standard definitions of covariance. And if you basically open this up, this basically gives you this equation. So this is what I mean by covariant. Here, if size are field independent, this is basically just the Lie derivative of psi with along eta. Okay, so I can now very easily show that this QR defined in this way is not a covariant object. Okay, just this is the proof. I simply ask whether this QR is a covariant object, and you see that it is not. It's just simple algebra. And because it depends on the variations of this phi r. Okay, so just to address what Suvrat just asked, the problem of non-integrability as well as non-covariance of charge in GR comes from the fact that we are basically linking two conceptually independent facts. One is covariance over space-time, and the other is covariance over the solution space. When you basically connect these two, basically when you interjoin these two, then basically you lose both of them, or either one, depending on your choice. Okay. And for those of you who have been thinking about this BMS type symmetries and so on, take phi r to be, for example, the flat space or asymptotic flat space. This is basically the variations that you would get when this eta is symmetry generator of BMS. And this basically tells you that this QR is not covariant because of this BMS charges. And this means that, for example, the mass, angular momentum, and all these are not well defined because of this ambiguity, if you wish, or freedom to define the basically metrics asymptotically up to BMS transformations. All what I'm saying is very sound and clear, but this is a very robust and formal way of stating this. Okay. So as long as if you're content with dealing with charge variations over the solution space, everything is covariant both on the space-time and on the solution space. But if you want to talk about the charges itself or even the charge algebra, then there are non-covariant parts which are coming from integration constants. Okay. And then I can now look back into the charge algebra, and what I get, please.
So maybe since this is an important point, I think I zoned out. What was your definition of covariance in this? So I was
yes.
through the time you were trying to integrate this, and yeah, what this eta I missed completely. Sorry.
Yeah. Okay. This is the Okay, so covariance is I had defined general variations over the space over any function, right?
Yeah, this is okay. Yeah, delta x.
And then I can compute this general variation over eta, which this is the definition. Okay, this is delta eta of something.
Eta is
and
a vector in the uh,
eta is a general vector, if you wish, a
vector
general
in the covariant
diffeomorphism.
phase space.
Yes, but you can take it to be a diffeomorphism just to
Okay.
keep things simple. And then if this is delta eta is equal to the lead derivative of x minus x when the lead derivative is acting on this psi, the symmetry generator, this is called covariance. I think this is just covariance means that under diffeomorphisms, things should behave like lead derivatives. Okay. Good. So this is the standard notion of covariance. But you can see that covariance is actually linking delta over the solution space and basically lead derivatives over the space-time.
And Xi was what? Xi is also some other vector?
Yeah, some other vector, symmetry generator, if you wish, but general diffeomorphism, if you want. Okay. So basically, the central charges that may appear in the algebras are also anomalies in the covariances in the theory that I had. Okay, so you can see that they are related basically to this QR. For example, for those of you who are familiar with the Brown-Hano setup, this Brown-Hano central charge is actually coming from the fact that we impose restrictive boundary conditions over the ADS3 boundary. One could have relaxed that, and then you get zero central charges. Okay, so it's important to know that to note this that even for the standard ADS CFT, there are restrictions that could be relaxed when we are talking about the allowed boundary conditions. Maybe if there's time, we can discuss this later. Okay, so far I basically told you that covariant phase space with fluctuating boundaries retains the covariance of the over the space-time as well as the solution space. The first one, covariance over the space-time, and this is related to Suvrat's point, is associated with charge conservation, whereas covariance over the field space is associated with charge integrability. Usually, when we link...
sorry. Shaheen, this point I didn't understand. I thought that charge conservation has to do physically with whether you have leaky boundary conditions or not. Why it's not just a covariance issue, right?
No,
the body mass is
it is.
Yeah.
The way I'm presenting it, it is because let's suppose that you have basically on the scry, you allow for the scry to fluctuate a bit.
Yeah.
In a precise sense, I can tell you what it is. But the derivative of a charge along this V, the V derivative of the charge is the news. And I can view this, the V derivative of the charge, as some diffeomorphism which changes the coordinate V. Okay?
Yes. Yes.
So, basically, this charge conservation could be viewed as basically something related to general covariance for the choice of V coordinate. That's lead derivative along some...
Sorry, just to understand, let's say we take the Bondi mass, not a super translation charge, just the Bondi mass. Are you saying that Bondi mass is not covariant?
It is not, yes. That's true. It's not covariant.
I see. I mean, that's a little confusing, right? Usually we would say the Bondi mass is a nice covariant because you have asymptotic boundary conditions, you can define...
Because you usually fix the time coordinate at the boundary.
Correct. That's right. So we fix the time. I see. But I mean, that's okay, right? Because that's an asymptotic boundary. So we don't usually...
Okay. So if you accept this, then it is right. But I want to free the boundaries and let them fluctuate. So I don't want to even choose that.
I see. Okay, but physically, you could, in your boundary, you could have energy coming in and out, right? So are you
Yes.
saying that you will never be able to define a charge that's covariant in this situation, or?
No, it is not. It's this basic problem of charges in general relativity. I'm not inventing that problem.
I see. Okay. Okay, thank you. Yeah.
Yeah, so there are two notions. One is conservation associated with covariance in the spacetime, and the integrability associated with background independence, covariant on the solution space. Usually we link them through choice of boundary conditions. As innocent as they look, basically, then the charge conservation and integrability go hand in hand, but they're two conceptually independent statements. We need not link them. And through this fluctuating boundary formalism, I actually allow them to basically be independent. Okay. So now let me, in the remaining 4 or 5 minutes, let me apply this formalism to black hole thermodynamics. So now, so far, this symmetry generators psi were generic. Now I limit them to be killing vectors, and I take the background to be a generic black hole which has a killing horizon. Okay, and by killing vectors, or exact symmetries, I mean delta zeta of phi. Phi is the generic field configuration is equal to 0. Okay. And now I apply my formalism, which extends Ayerwald in several different ways. Okay. So this is the basic setup. Let's suppose that I'm considering two generic codimension 2 surfaces, S1 and S2. They're related by a codimension 1 surface chi 1, 2. This chi 1, 2 could be a time-like, space-like, or null separated, these 2 points. So this is quite generic. And this 2 dimensions is basically suppressing the S part, and this is only the B and C part of the space-time. So this is just 2-dimensional. If you wish, you can think about this as time and radius in, for example, Schwarzschild type black hole solution. Okay. So this is the basic setup. Now I'm going to compute the charges over this S1 and S2 and compare them. That's basically the proposition 1, which is the generalized small relation, is that I compute this Noether charge, which was the integrable charge for S1 and S2, two arbitrary codimension 2 surfaces for a given vector zeta. The difference between the two is related by an integral over this surface chi 1, 2, which connects S1 and S2 over the Lagrange. This one can basically prove this given the expressions for the Noether charge and so on that I showed. So when you open this up and write it for zeta, which is creating the killing horizon, you get the small relation. But this is now a very covariant version of the small relation. Okay. If you take this psi 1, 2 to be radially or separated, so that's basically space-like separation. For that specific case, you get small relation. Okay. The second proposition is generalized first law, and that's I define a 0-1 form K in this way, which is built upon the Noether charge and this theta simplicity form. And one can show this. This is the statement of the proposition that this K is independent of S1 and S2 for any zeta, any killing vector. And again, if you open this up for S1 and S2, which are radially separated, you get standard derivation of Ayerwald, but this is much more general than that statement. Okay, the two propositions are 3 and 4 are needed to basically show that these equations, generalized first law and SMAR, are independent of W and Y freedoms. Yeah, so that's basically while the Noether charge could be depending on Y or W, this expression is covariant, so it is independent of Y or W. The changes in the by Y or W in the left and right hand side are exactly the same and they cancel out. So this expression is independent, so as this expression. So these are ambiguity free. You can see the paper for the proof. Let me just show you, this was very abstract. Let me show you one simple example. This is, of course, like killing a mosquito with gunshots, but that's okay. Just to show how it works. Take this zeta h, which generates the bifurcate killing horizon, and zeta t and zeta phi are the two killing vectors associated with time or axis symmetry. It vanishes at the bifurcation surface, just by definition, and it's null. So at the horizon, it squares to 0. Now the point which is usually overlooked and is related to one of the first questions I was asked, this kh, which is the surface gravity, and omega h, which is the horizon angular velocity, both depend on the parameters of the solutions, like M and A for the Kerr solution. And in my solution space, I'm allowing for all the parameters, initial data, whatever, to fluctuate. So I'm not considering cases where in my solution space, everybody has the same M and A. So among the delta phi's that I have, M and A are also allowed to fluctuate because this is the set of all solutions. And Ayerwald's derivation just doesn't work for the cases where you allow for the parametric variations. But our formulation actually works very well for that. So just to show how it works, I just rewrite my first law, which was this. Choose from S1 and S2 were generic and still could be generic. But just for the standard derivation, you can take S1 to be the bifurcation point and S2 to be the I naught. Okay. And this is basically giving me the standard first law. Just to sketch you through the discussion. When you compute this, the left-hand side, when you compute it over K over the SB, the bifurcation surface, this gives me the delta S H. This is the variation of the Wahl's entropy. But the point is now if you go through the computations, which is straightforward but lengthy algebra, when you allow for this TH and omega H also to have fluctuations, basically the very definition of this K gives me the fact that all these variations just drop out, okay? Which does not happen for the Ayerwald derivation. And basically, you can go through the algebra and then basically define the ADM mass or ADM charge, and you get this first law. Okay. So this is very formal. Sorry if I'm for the time, I'm just going quickly, but I'll be happy to discuss after the seminar. So this is basically, let me emphasize again that the first law that I wrote does not depend on the presence of a bifurcation surface, or the other S2 need not be I naught. You can put this S1 and S2 anywhere you like in your spacetime, and you still have this equation. So this is very extended notion of first law. And as for the small relation, this is, I think, to my knowledge, the first and the most rigorously covariant derivation of the small relation. Again, you can just simplify things by taking S1 and S2 to be the bifurcation surface and the I naught. And this is the expression for the first law. You need just to go through the algebra, plug this zeta H, and compute this side and the other side. And you can find the details of the computation in our paper, and you get this equation, which is the small relation. Okay. Let me move to the concluding remarks. As I just discussed, covariant phase space, when you allow for the fluctuating boundaries, it leads to conserved surface charges, which are always integrable, but they need not necessarily be conserved, because conservation is linked to a very specific fixed notion of time. You showed that the time derivative of something is zero, but that when you allow for the boundaries to fluctuate, that the very definition of time itself should be revisited. And going between two different Cauchy surfaces, for example, is or could be related to choosing different time directions. And this is how actually, when you allow for the boundaries to fluctuate, you can absorb conservation into integrability or non-integrability. So, but the point to emphasize here again is that the notion of integrability and conservation are conceptually independent. So, and when you want to specify about the charge, when you want to specify the charge itself, not the charge variation, you inevitably break covariance, either on the solution space or on the space-time. And it's your choice to choose whichever you want, but you cannot keep both. Charge variation is fine, but the charge itself is not. And this is how basically, I think the whole notion of defining conserved charges in GR, the main discussions in the literature have been misguided, because they forget about background independence and only focus on one. And this is how they basically miss both. And then here I focused on, for example, S1 for the black hole case. I focused on the case where S1 and S2 were space-like separated, but I could take S1 and S2 to be time-like separated. And this will give me a new notion of, you may call it still first law, for the cases like ADS space, where a natural choice for S1 and S2 are two different points at the causal boundary of the ADS, or even for the flat space in the asymptotics, S1 and S2 to be 2 points on the scry, or 2 points on the future horizon. So they could be null separated. And when you take them to be null separated at scry, this will basically give me a new intuition of the balance equation, Bondi balance equation, or what's very much discussed these days, the memory effect. So memory effect is basically, it could be very easily or more rigorously described through the formalism that I just mentioned. And last point, which is, I think, very important, and still I need to understand it better, but I can share you the idea. In my understanding, some of the issues related to information problem of black holes is associated with the fact that we always think of a black hole who is Hawking radiating to have a fixed bifurcation surface. We may allow for the horizon to fluctuate through standard Hawking radiation, but always we keep the bifurcation surface to be non-fluctuating and intact. And I can discuss it further if you're interested in. I think the key issue to understanding or addressing information problem is to generalize the setup such that the bifurcation surface can also fluctuate. And our formulation allows for this. And I hope that this will shed a new light also on the information problem. Thank you, and sorry for going over time.
Just a question about your last point. I mean, for evaporating black holes, for a black hole that is formed from collapse, there anyway isn't a bifurcation surface.
That's right.
So what does this mean?
But the horizon has an endpoint, past endpoint, right?
Okay, but that's not a bifurcation surface, right?
No, that's not a bifurcation surface. So the point is basically whether there is a point on the horizon that we keep fixed in this setup. And the very rough picture or point is basically when you allow for black hole to evaporate, in the end, there is no bifurcation point either, right? You lose everything, including the bifurcation point or that fixed point on the horizon. If you have any fixed point on the horizon, let it be bifurcation point or the past end point on the horizon, then basically in this setup, you're not apt to describe evaporation.
Okay. So can I also ask a question related to this last thing you said?
Please.
It seems to me that the most important issue in the information problem is that, the classical intuition is sometimes misleading. And I'll give you an example, and then I want to ask about your, for instance, the way Hawking phrased it was he said there's a no-hair theorem, right? Which is that you fix the charge at infinity, and that fixes the bulk because of a no-hair theorem. However, in the quantum theory, it's clear already that that can't be right. For instance, if you consider a black hole which has canonical spread in energy versus a black hole that has microcanonical spread in energy, they have the same value of expectation value of energy, but they have different values for expectation of m squared. So you already see there's no notion of a black hole geometry, and the no-hair theorem is just false. And
okay.
You see, but isn't it clear? Because
no,
both of them
it is clear,
the same
but
classical geometry, but yeah.
So while I agree with your statement, it's not a problem for the setup that I mentioned here.
Yeah, so I wanted to understand. It seems that the key issue is this: is that you have to think of spacetimes where the charges fluctuate, where you have to think of spacetimes which are superpositions of different charges. And so, is there an actual quantum generalization of these charges that you have? Because it seems to me that's the key issue. Like that's the error in Hawking's argument. It has to do with this.
That's a very good question. So at least my understanding of the information problem is that it's a semi-classical problem. It's not a problem to full quantum gravity. It arises there and it should be probably addressed within the same setup. Okay. So I'm now, all the statements I'm making now is within this framework.
Okay.
So this is the usual dogma, right? Okay. And
yeah, we are addressing it there. I mean, this is a gravitational effect already tells you have fluctuations of charges.
Okay. So
so maybe my internet is
okay. So this can
sorry,
I hear?
maybe
Can
my
you hear?
internet went off. Yeah.
Okay.
Yeah, sorry, it's
okay,
my
so
problem.
my comment is that I need to redefine what semi-classical means. So for me, where I have some boundary, even if it is fluctuating, and then I have modes in the bulk. By semi-classical, what I mean here for the right, this is, I think, what's the right setup for this information problem. I quantize the boundary degrees of freedom, but keep the bulk gravitational waves classical. Okay. And
then you will not, then there will be a problem, right?
No, it is not, because I'm including the data at the corners as well. In your description of what Hawking said, you implicitly did not include this.
Okay. I mean, isn't it inconsistent in perturbation theory because you're ignoring effects that are already visible at next order in G Newton? But the information loss is a question of exponential effects in that, right? So why is it consistent to look at this setup where you have a background classical geometry coupled to a quantum field?
Okay. Well, of course, I don't have the full answer, but I can give you how I would try to formulate the problem in this setup. Okay. So far, this was pure gravity, so let's stick to this. But it obviously could be extended to cases where you have other degrees of freedom. So basically, the point is here, all the information about the bulk modes could also be encoded in the boundary modes, and which are labeled by these charges and their variations. So if I follow them, I have all the information about whatever which is going in the bulk. And if I can consistently, this is a big if I can consistently quantize the solution space that I just mentioned here without even encoding the bulk modes, then, and I don't need to have the bulk modes explicitly in this construction, then the only thing to address the information problem is not the details of this quantization, but the very fact that this Hilbert space and the symplectic form that I think is well defined over the solution space could be, if it has a finite volume, the solution space, and omega is basically giving me the symplectic form over this solution space, that if it has a well-defined and finite volume, that's enough for addressing the information problem. And so that's how I would try to formulate this. So I will try to quantize the boundary data, boundary plus initial data, and let the bulk modes to be just classical as it is. That's how I define semi-classical in this setting. I know I didn't answer the question. I just told you how I would think about this.
Okay, thank you.
Okay, can I ask one question, Shaheen?
Please.
Yeah. So just a quick question. First one is a quick clarification about what do you mean by background independence here? I mean, is it just coordinate independence or something else?
No. So basically, in this specific setup, and so the first thing is just the standard textbook definition that all the backgrounds where all the other fields or physics is formulated upon is a solution of the same theory. I don't need to specify a background to do the formulation. But what this means for the charges and what I discussed here is that to specify the charge itself, as you can see in the slide, I need to specify this reference point. The charge variation over the solution space does not have this problem, but when you want to talk about the charge itself, you need to fix a reference point, and fixing this reference point is breaking the background independence, obviously. But my point was that this not only breaks the background independence, because you can see it depends on the specific background, it also breaks covariance, because I just defined the covariance and I showed that this QR is not covariant. So basically what I showed is that charge variation is fine, covariant over the space-time, over the solution space, but the charge itself breaks background independence because it depends on the reference point, and as well as breaking covariance. This happens both.
Okay, so the other question was, so as you were allowing fluctuations of your boundary condition, basically boundaries. So like, as you mentioned once that there can be a null boundary at Sky plus. Usually when you fluctuate that might become non-null in general.
Yes,
right?
That's
so
right.
You are allowing our null infinity to become space-like or something also in your setup. Are you saying
Locally, yes. These are local small fluctuations around that, and there is a very subset of this general fluctuations that keeps this null, and that's when you allow for just scaling the radial coordinate by a w, right? As general function. Okay, but
so
there's
in that case, the solutions, I mean, some the black hole solutions will have some problem, right? I mean, how do you define the causal past of a null infinity? How do you define globally what is the black hole spacetime, etc.? Or you are saying that it's locally you can always
yeah,
fix it.
that's what I'm saying.
And then the way you have just renormalized, I mean, sorry, you showed the integrability of charges by taking some fluctuations of your intersection of Cauchy slice with the boundary, right? You have taken the fluctuation of that particular. So
Yes.
can I understand that by saying that since you are allowing some non-trivial boundary conditions in some sense, then you are some sort of allowing some kind of matter or so-called stress energy tensor at the boundary, which is actually making your action and other charges, etc., well defined.
It's a good question. So I didn't discuss that here, but that's what in part we have studied, and we are studying, continuing that on that. So that you could have asked how this is related to Brown-York stress tensor, the charges that I defined here.
Yeah, I mean, some sort of.
Yes, so this is going to be an extension of Brown-York charges where I allow for this S to also fluctuate. In the standard Brown-York, they do not allow for S to fluctuate. Okay. And for the case where you are on Scry or on the ADS, this typically becomes infinite, as you know, and you need to regularize this. But the point is, when you write equations like the ones that I was interested in, like this ones, for example, in 2 or in 4, actually either side may be infinite, but the infinities actually cancel out. I don't need regularization when I want to compare two things at two different S's. Okay. Individually, maybe either of them is infinite because I'm allowing for the boundaries to arbitrarily fluctuate, but the difference remains finite. In particular, for example, this right-hand side could be infinite, this other term could be infinite, but the infinities are exactly the same and they cancel out. So we have given examples in our paper. It's sort of non-trivial, but it happens.
So one related thing is that usually in asymptotically flat spacetime, you get BMS symmetries. So those are those symmetries can arise if you put a special kind of boundary conditions only. I mean, so are you saying that if you can still allow more generic boundary condition and get away with these charges and other things?
Yes, of course, yes.
Okay.
And actually, this has been done. So a part of it is our work. Others have also contributed, like Friedel and company. So there are some various extensions of BMS. They call it generalized BMS or WBMS.
What I am saying that generalized BMS and others, those standard things are there. Can you come up with some other example where the boundary conditions may
I meant that, for example, for this specific WBMS, they also add the generator, which is scaling the radial direction arbitrarily at infinity. This is an extension of BMS by one extra generator. There are other extensions as well.
So you have examples of
Yes.
such,
Yes.
okay, in your
Yes,
paper.
yes. So BMS is not the most general, of course.
Okay, so one last question maybe. So this has to do with your construction that you cut off the space-time probably, and you say that I am defining the theory in a box and then
allow for the boundary to fluctuate arbitrarily. So I don't cut out anything in the end.
Yeah. So, but when you are saying that I am defining my theory on MB, the manifold that you have defined, so aren't you specifying a particular embedding to your general manifold that you are considering? Like here, this picture says that it's a kind of a cylinder, right? Isn't it?
But it is arbitrary. It's arbitrary. So had I fixed this boundary B and C, you were right. But I do not. So this B and C are just some functions which could be changing. Like I consider delta C and delta B, right?
So you are saying that for any arbitrary embedding function, this will work.
Yeah, exactly. That's what I'm saying in the end. That's exactly true. But I think I chose this setup to discuss because I didn't want you to be concerned with what goes in asymptotics and you have infinities and so on. You may be worried about things that may become infinite there. So this was the purpose. But this is even an extension, as you just mentioned, of the standard BMS boundary conditions in the end.
Okay, thanks.
I think there are no more questions. Thank you, Shaheen, for patiently answering all the questions.
Sure.
Thank you, Shaheen. Thank you.
Thank you for having me. I hope it was useful.
Thanks. Yeah.
Sure. Bye.